And thanks for coming to the weekly meeting again, guys and everyone. Just a few quick things on my thoughts before we get going. I was thinking of hosting another, I'd like to host another, Friday afternoon session where we can either code, or if we don't feel like coding, we can, do some games or something in the afternoon. Just playing around, socialize a little bit next Friday afternoon. If everyone is available for that, you're welcome to join. Probably similar times that we've been doing in the past. Maybe start with a little bit of coding and then move on to something else afterwards. Any other quick agenda things to set out from anyone? Going these matrices. Okay. With that, I see Devin has some quick reports. Moving on.
Yeah, just taking all the feedback from the tutorials and theory stuff from Discretize and chipping away at that. So made a lot of progress this week, but there's still work to be done before the next review. And then I put some work towards finalizing our PR for getting EM1D stuff into SimPEG. So yeah, all that stuff, updating tutorials, updating tests, partitioning it out so that it fits with our SimPEG structure. Still some work to be done on that before it's ready for review, but yeah, progress is being made. I don't think it'll take too long, but there's still stuff to do.
Exciting. I'm glad. Looking forward to getting it in. It's mostly, so it's just, it'll be a good thing to get in there. I think a lot of those specialized routines would be well served as utilities for using that.
Yeah, I'm thinking about that. There's some interesting stuff with waveforms and systems, and it's kind of a legacy for when it was its own repository. I'm just trying to find the best place to put it, and whether or not maybe some of the functionality could be needs to be altered to be more SimPEG like.
Mm-hmm. Understandable. See, John has a few things next.
Yeah, still plugging away at that MT pull request. I found some frequency domain stuff. I think it's on the EB formulation, and the analytic tests are failing. So I've been digging around trying to figure why those are breaking right now. And then I've been working on the tiling a little bit. Yeah, kind of put the MT down because that was a little bit more appealing. So I was just testing it with the NUMA node kind of theory we had, and it's kind of see that if you can squeeze out, you can scale up by adding more tiles, but if you want to really get some more gains, you just keep adding a NUMA node to your work, as a worker, and you can start to get orders of magnitude faster that way. And so the way that I've done that, though, I can squeeze out a little bit more. As you see, if you go up to 30 in the plot there, you can get more out of just whatever NUMA nodes you have. But I can't seem to do that with Dask. Dask seems to kind of just, I guess, optimize just to, you can get about an order of magnitude out of the way that we do Dask right now. But I can't squeeze it out because I can't mask. You can't really tell you can't set the affinity for the CPUs in the scheduler, or in the workers. So you can't quite squeeze it out enough. But I'm working at it. I think there's a way that you can still with Dask. I just got to dig around and find the right config.
Gotcha. So I might be uninformed here, but what is a NUMA node?
So the NUMA node is pretty much the memory controller for a CPU. So a CPU can have 10 cores, but it's only got one. It might have two NUMA nodes. It might be broken down into two, but most CPUs have one NUMA node that controls all the memory, and all the processors go talk to it, and then that's what talks to your RAM. So you can become bandwidth limited within the CPU itself, because it's not each core has its own memory. it's all being accessed through that NUMA node.
Okay.
Yeah. And actually, Dieter, I was going to ask that really quickly. Playing around with Paradiso there, just testing it by itself on a machine that's not Intel, I found, yeah, the performance is terrible. Like it's not that good. So were you able to compile Paradiso with OpenBLAS? I thought you were talking about that one time. Yeah, Dieter, sorry. Yeah.
Me, no. I just run into the issues when I try to run similar big size model with SimPEG than with my code, and then it for big models it just blows up. But I didn't never try to compile or no.
Okay.
That's when I just wondered once if anyone tried the new Paradiso version, like an academic license or no. But I never did. No.
Okay, nice. Yeah, no, I thought there was a post about that a long time ago, because yeah, it's actually significant. Like if you run on an Intel machine, Paradiso runs really nicely, but if you put it on, say, those AMD Threadrippers, yeah, it's like double, like much time, like twice as much.
So Intel is doing that by design. I mean, I've read about this before as well. What happens is that Intel specifically disables a few of the vectorization routines that it can use, like the processor vectorization routines, and some class on the MKL.
Yeah.
So that's what really slows it down there. On older versions of the MKL, you can set an environment variable that kind of triggers it to get around those, but they've since removed that on new versions of the MKL.
Oh, good to know.
I can't remember what it is and at what point it stopped working, but I knew there was a way to get around it at some point.
Oh, fair enough.
It's all the like SSE3 vectorization instruction sets, like those higher order or more fundamental routines like that are just disabled.
They're just disabled. Huh. Yeah, maybe I'll look into it a little bit there, but yeah, Intel chips are usually nicer anyways. That's about it.
Cool. Losing where is this meeting notes are at. Okay, Thibaut. See Thibaut next.
Oh yeah, I didn't do much in terms of like contributing to SimPEG lately. Like with the only like very minor thing with Dieter, we updated the badge in the README. We added Dieter added the Conda Forge version, and I replaced the Travis badge for the Azure Pipeline one. So the README badges are up to date.
Cool. I had done that with the discretize. I just forgot. I just slipped my mind with the SimPEG one. So it's good. Thanks for getting that. Shalong has a few notes in here for the quick reports.
Yes, I don't have too much report at this moment. I'm still working on the tutorial and the example for the cross gradient. Also, one of my colleague, Kenneth, defenses his thesis, master thesis this morning, and I was taking charge of his inversion code. So I think maybe his work can also be contributed in the SimPEG research. I think that's all from me.
So I have been working with Lindsay and Dieter on, again, on the MT1D with boundary conditions in the EM. It's going along really well. It works like the boundary condition things that I was testing with discretize, those little routines seem to be working well for that problem. I've dropped a link in the IOXA notebook to the cell in the notebook that I have a question on. Can I like to bring it to you guys? So if you look at this system, the issue that I'm having is the system doesn't necessarily make a symmetric matrix for factorization in 1D and 2D. We can get it to be symmetric, and there's two kind of options that we can mess with here. So the first is that if you look at it, we can no longer just pull where, if you're looking at where the A equals line is, on the right, something gets multiplied by the inverse of the, like the mu inverse matrix, but it doesn't get correspondingly multiplied on the left. So it doesn't make a symmetric matrix there. In the past, we haven't had to worry about that. It just gets moved to a different side. However, with the boundary conditions, it does make a difference. So our options are either to just multiply again by this matrix on the left, or do a weird system. I can show my notebook really quick here so you can see what I'm talking about as well. So I'm talking about this line here. So on the right, we end up multiplying by this matrix. So we have two options here. Either we can multiply it by on the left, on both sides. So it'd be on the right-hand side and on the left-hand side. But I don't quite know how this will handle as far as the condition of the matrix, the condition number and stability of the matrix. I'm not sure how well it'll do with that. The other option is
hey Joe,
yeah.
What is at? It seems quite new to me.
This is
that like a?
It's specifically the matrix multiplication operation in Python.
Oh. Oh,
so with sparse matrices, it's the same as multiplication. But if you had a NumPy matrix or NumPy array,
right, it doesn't. Yeah, it just does an element-wise operation, I guess.
Right. So you could do A at B, and that would be matrix multiplication.
Actually, that's nice. Cool. Didn't know that.
Yeah. So we can anyway, our options like this. Like I said, I'm not sure how that'll handle stability of the matrix. The other option is to pull this matrix out on the right-hand side, but that kind of leads to a weird, like odd solve operation. So if we pull this out to the right, see mu, we need to multiply down here by this. So this would this system is similar to what we've had before, but we have to do it this way. There's no way you can, if we multiply it over here, it doesn't work properly. Because the system that we're actually solving at this point is that A times I guess this would be multiplied by mu. So this, I'm just kind of curious what people have any, we end up doing a similar sort of thing when we multiply by V as well in a different, so this is the TM mode. In the TE mode, we have to multiply by V on the left to get a symmetric matrix in the formulation. And I'm just trying to avoid having all these like double mu terms and also if we do this, if we do it the other way, the derivative's weird, but then again, the derivative is odd here as well.
What was the problem of just making A symmetric? Like you mentioned that, I don't know, like a singular.
I'm not sure how it has affected the condition number of the matrix yet. I just don't.
Yeah, I don't really see the problem there. And obviously, if you're making like the matrix symmetric, that would make the condition number better, I guess, than unsymmetric matrix, I guess. That's my intuition. So I think that's what we typically did, just making the asymmetric, and rather than multiplying something after you solve. Yeah.
Okay, just looking for input on it. That was it. And I've linked that notebook cell into the notes here if you guys want to look at it as well. Thank you for that. The 2D MT should be following pretty shortly here. And then I also had a question. So I'm not very well versed on the differences between the MT conventions in SimPEG versus what it's expecting, like in all of the outside stuff that's getting put in. So I'm fairly confident that this is internally consistent, meaning that it gets the accurate Y and like EY and BX field, and that the signs are correct within our right-hand coordinate system.
Yeah, it won't be consistent with what's common for people in practice.
Right.
And yeah, that's something I've sort of considered a lot when working with GIF tools and things. So I think we just need to have a good function for reading in and writing out stuff for particular conventions.
Okay.
And yeah, I already did all the, making plots and figuring out which convention you're in, because that's something you have to do every time you look at MT. So we just need to kind of make a version of that for SimPEG, but it shouldn't be hard.
Yeah. And then John and Lindsay, if you look in that notebook, I put in the derivation, like those equations, just to double check. So I'm like, the full derivation is in those notebooks, and that I added it to that notebook that Lindsay had shared.
Nice.
Okay. Because just double, I'm trying to remember. So in a 1D Earth, it's 45-degree phase, like for a 1D homogeneous Earth.
Yeah.
Like it's 45 degrees for, I don't, which it's a ZXY or ZYX.
Yeah, it all depends if you're in a Z positive down or Z positive up, or if you've chosen to do the plus I omega t or the minus I omega t. It all impacts it.
Gotcha. Okay.
Putney is a good person to ask for that too, because he went through all of that initially when getting everything set up with SimPEG.
Yeah. Well, you can also, for the GIF Tools cookbook, I kind of did this. There's a table, and it kind of says, if you see this phase relationship, this is the real and this is the imaginary component of ZXY, then this is probably what's happening.
Gotcha.
Yeah.
Sounds good. Well, thanks for that.
Yeah.
I go through again and double check the biometric part is correct. Like the sign on it is consistent with our convention.
Do you have any intention of putting in the nodal inner product matrix? I'm just going through some of these basic tutorials for discretize, and I mean, we don't need it to do, to maybe add physical properties and stuff to it, but just to be able to call nodal inner product matrix.
I mean, I'm trying to think when it would be. We have to use that because most of the time, like in nodal formulations, we end up taking edge editor products, right?
Yeah, there was I think there's a problem I worked on once where I was solving like a magnetostatic problem in terms of potentials, and I remember having to use it. Or I guess, can you guarantee me that someone doing a completely independent project of electromagnetics wouldn't have to use it?
Right. I guess.
No, I think there is a use case.
Yeah.
Of nodal product. So if anything is defined in the nodal, and if you need to integrate it, then yeah, you need to have a nodal.
Yeah. Like I would, if we had a nodal formulation for the, like for that 1D MT system, right? We would be doing an inner product on nodes on a few things here.
Because would it? I mean, would it? Do you think it would take a long time, or do you think it'd be pretty quick to just to get that in?
I think we could get it in.
Yeah, because I am actually using it on one of the tutorials just to show that if you were to take inner products between two scalars, you could do it at cell centers or you could do it on the nodes.
Yeah, we can get that in. So that's about all I had. Lindsay, did you seem like you have some things to say?
One quick update is I connected with Jared Peacock earlier this week. He's at USGS for folks who don't know him, and he does a lot in MT. They're really curious to just kind of keep a pulse on what we're up to, and so maybe once we are kind of happy with the state of the pull request and have a few examples and things like that, it'd be great to reach out. They've offered time on the USGS HPC Center to try things out. So if there are examples that you have that you'd like to try out, particularly if it is MT, because that is directly in line with his interests. But if not, if there's other aspects of SimPEG, it's something that like we could probably have a conversation about. And then the one example that he mentioned that's particularly of interest is actually the 1D. And having a bit more flexibility there to use that to perhaps build up a starting model. A lot of other 1D codes have, like you actually really solve the inverse problem really well, which isn't necessarily what you want for a starting model. And so there could be some interesting applications in kind of thinking through like if we do sort of a spatially constrained 1D MT inversions and early stopping, what kinds of things would you want to do, perhaps using the 1D to build up a starting model for a 3D. So just wanted to flag that if that is of interest to anyone.
Yeah, well, we had intentions of doing the stitched 1D for the MT stuff once we get 1D EM1D in.
It'd be nice to have the tiling done too, to test or to throw onto the center, because that's where we're actually going to get our gains into what other codes can do with MT.
Yeah.
If we can start solving over frequencies or parallel frequencies, then yeah, we'll be right in line, I'd say.
Hey, John, I was actually curious. So like you guys are storing the sensitivity. That's sort of the philosophy of using Dask at the moment, I guess.
Well, oh yeah, sorry.
Have you thought about, let's say, so their HPC would likely have a multiple nodes. So you have a physically multiple nodes.
Yeah.
And what I wasn't sure, you store a ZAR file at some point, and now actually you not only have a single computer, you got multiple computer. So you would likely distribute that ZAR file into multiple files. Have you guys kind of played with it at some point and got some sort of plan how you handle like kind of that case?
Well, if we just pass back the vectors, the ZAR file can sit on the node. Like it'll just write it there, and then whenever we need that vector, it'll be passed back. However, I haven't tested with that quite yet, because I'm more on the side is like we have all the RAM we need, like at DS. So I've just been throwing RAM at the problem, and I haven't really been storing it on most of my tests. I've just been putting it into RAM. Yeah.
Okay. Got it.
But yeah, the idea would be it would just it would just stay on that node, and we would access it from there, kind of thing.
I see. So you're gonna likely generate the multiple ZAR file and then store at whatever node that you assign. That's sort of the idea.
And then it'll ask that node for that piece of the J from that ZAR file sitting on there. I believe, I don't know, Dom, you kind of came right in the end, but I think that's the plan. For storing the sensitivity with ZAR, it would just, if you send it to the worker, which is a node, it would just write it there, and then we would just ask for the information back, right?
Yeah, that's our hope, right? Because we're basically going to give them a local, like say, I'm going to tell the worker, here's a simulation, go compute J. And then once the worker has it, then technically the toZAR should be a local write. That's the thing we need to check, right? To make sure that it is a local write. Otherwise, we might need to really specify like, this is a location that you want us to, that we want you to write it, but we'll see. Hopefully the worker just grabs it and writes it locally. And then that's, yeah. And just returns dpred at the end, or the JVec vector, right? So nothing else is sent back.
Right.
So Dom, I know you kind of came in at the end. Did you have any updates from the past week?
Yeah, so I, you know, trying the bigger problems, the bigger DC problems, and starting to encounter the issue that the storing each meshes of each tile is starting to, you know, weigh a lot on the actual process. And we don't really want to send the 3 meshes across the network, right, from the central node to the workers. So I started looking into getting rid of the mesh on the simulations. So basically, the simulations will be only storing the operators that it needs to do the things, and then just drop off the mesh right away. So for right now for DC, it's pretty simple. We only need to store the projections and then a gradient and a divergence operator, and then we can just flush out the mesh. And then that really reduced the memory consumption, right? And as I said, we won't have to send the 3 mesh across. So we'll have to see how easy it is for the other simulations, but I don't see why not. That would be my suggestion to the group.
How does it handle like the inner product matrices?
Yeah, so for the inner product, all it really needs is to hold the projection, right? Let me double check again. I can't remember on top of my head, but it's possible to just store the operation, to just store the operator. Let's see. Well, we can go over it later, Joe, but it wasn't a big issue.
Okay.
Yeah. Where's the? Can't remember where it's stored. I'll have to dive in. I remember having to look at it and then going down the code, and it's like, oh, okay, we only need to store that part, right? But I'll look it up.
Yeah, I was just kidding. I know a lot of the other codes rely on the mesh to keep updating the inner product matrices.
Oh yeah, I know. So when it calls the inner product, it's just a mass matrix and the gradient operators, so we can basically do it without the mesh.
Mm-hmm.
Yeah, we just need to store the essential. Basically, that's what I'm suggesting, because really at the end of the day, we don't need the entire mesh, right? We just need a few operators. Basically, that's the idea.
Or like can we just do it on the fly? Like do we really need to store? Because I think the forming that matrix is pretty cheap.
Yeah, but
I guess like
we still need to keep the mesh, right?
Not,
sorry, go ahead.
If your local problem is not that big, then just why don't we just do on the fly? Like why do we want to store?
Well, we just don't want to store the mesh, right? Because the mesh is expensive to hold.
Right. So my point was like, oh, I see. Creating mesh is expensive.
Well, creating the mesh is not expensive, but holding the mesh parts, right? We need to remember all the nodes and all that stuff. And once we compute the operators, it stores the volumes, it stores like all the extra stuff, right? We don't really need it after we calculate our operators. Yeah.
Yeah. So my point was then why don't we just like generate on the fly? Like we just don't store it. And
no, that means every JVec will need to reform a new mesh, recompute the operators. It's going to be way more expensive.
Okay. I thought like if that's not expensive, then I would.
Oh, the operators are not expensive, right? The operators is like if a few integers for the location and maybe 1 float, you know, per cell. That's pretty damn cheap.
Right. But forming it is expensive.
The expensive, when you say expensive, it's not really in compute time. It's really in how much RAM we need to store and pass over the network. We want to minimize the amount of stuff that we're moving on the network, basically, and holding on the central node.
So on the central node, then do you hold like every mesh is held on a single central node?
If we keep them, yes, that's the idea, right? If we don't have to keep all the tree meshes, we just create a simulation, prime all the operators, and then flush the tree mesh, right? So now we're only having light simulations that we can move over. Yeah.
Did you? I thought at one point you were working on building the meshes locally on each node.
Well, the thing is that we can't guarantee that nodes will keep anything in memory, right? Yeah. We could technically build a mesh, store it on drive, and then fetch it back. But I don't see the point really, because at the end of the day, if we're going to form a mesh, right, and then store operators on the mesh, it's just more expensive. Why don't we just keep only the operators and don't keep the rest of the mesh? Right? Because the mesh, once it's formed, once you ask for the gradient or the mass matrix or whatever, it holds it, right? It holds it onto the mesh, and then the destinations just go get it. But we don't need to keep the whole thing. And anyway, so now we ran some huge problems. Did it against DCIP3D, and we went from like an hour and a half per iterations down to like 7 minutes. It's like wicked fast. And this is not even without tiling. This is just like just storing J and lighting up all the operations. So that's really promising. Quite excited. John and I will be testing it on a data set for my client next week, I guess. And yeah, it's quite promising. Future is bright. Pretty excited about this.
What system were you running it on?
Again, coming up.
What kind of system were you running it on?
On my laptop, 12 cores, 7 minutes.
Cool.
Really good. Really good.
So you're saying that DCIP3D was an hour per iteration?
Yeah, an hour and a half. Yeah, the old code, right? But at the same time, it's just redundant. We're just removing the redundant operations. There's like too many matrix vector products and then factorizations or backsolves that are done over and over and over again, right? Every CG, you're doing it like multiple times. And just the fact that we can convert all this to like a single matrix vector product, that's the gain. It's killer quick.
Yeah. Yeah. It's interesting because when we were learning from LDAT, the idea was never form J, and now we're going back to forming J. And I agree with them because that's actually expensive. Like that, not forming J is not cheap. You need to solve that a lot of times.
A lot of times.
Your C iteration, like it's actually a lot. So the number of solve, I think it's not just 100. I think it's at least a couple hundred times that we need to solve the force system, and that could really slow down your inversion. Anyway,
but I mean, there's a good reason, right, that LDAT didn't want to form J, is that before J needed to be full in RAM, right? The whole thing needed to be stored in RAM. But now we're using the new development is that SSD can act as RAM, and we can just parse it out chunk by chunk, and so that's the gain. That's the game changer.
But let's say it's just a hypothetical situation. Let's say you're doing a seismic inversion. So you got if you want to really form J, you need a huge hard disk. Let's say a couple terabyte, and maybe even more. And do you think that would still work?
I think we need to be smart about it. That's where the tiling really comes into play, right? Is that we don't need to have a sensitivities that span the entire space. We can just localize it, and that's fine. That's the other level, right? So there is the storing J. That's a huge save up, and then the other layer is like tiling. Let's be smart about where sensitivities live. So yeah, of course, eventually we'll hit a bottleneck, you know, but we're making progress. We're advancing.
Oh yeah, I like that. I like that idea. And then actually forming J has quite a bit of advantages. And then you can also get some good properties.
I know. We have a killer preconditioner.
Yeah, because actually it's a good point, because once you like start overing a couple million cells, the the current preconditioner that we're using, our regularization function, it's actually quite expensive.
Yeah.
Anyway.
Yeah, absolutely.
Have you done tests like comparing the number of solves between the two kind of things, like as far as completely forming a J matrix as opposed to doing it implicitly however many times is needed?
The results are identical, right? It's the exact same results if you store it or not, because it's the exact same operation, right? Just the only difference is that one we're storing it and the other one oh, sorry, go ahead. Yeah.
I meant like counting the actual number of CG solve, or counting the number of matrix solutions.
Counting the number, oh, we could do it by hand, right? Yeah, and that's going to be for each problem, it's going to be different. But
right, so it's like, okay, well, yeah, we're only doing JVec. We're doing that JVec multiply J transpose vec however many times for a CG iteration, right? Like once per CG iteration, and then we're doing, you know, I don't know, however many CG iterations. Like we usually cut it pretty short, don't we?
Yeah, we cut it pretty short usually because that's the expensive part, right? So it was like, oh, we're gonna do 5 CGs. That's enough. Let's quit. And that's dangerous because we don't know what we're minimizing if we do this, right? Whereas now we can just solve CG all the way to precision. You know, 1 to -4, whatever. Solve it. Now we have a real Gaussian step, right? We're not cutting it. So that's pretty good for us too.
Yeah, I'm actually curious, like testing a DS data set, because now you got lots of data. So the disadvantage of forming J when you got lots of data. So I think the number of solve, like I'm not sure which one actually wins, because in that case, because you got I don't know, zillions of data, that's the number of solve that you need to do form J. Anyway. I think that seems like a good example to beat. If you can beat that example, and I don't know, that's probably the way to go.
But that's an interesting part, right, Sag, is that when we're forming J, when we're storing it, it's the same amount of work as doing basically a single JVec operation plus the storing part, right? Because we're all doing the same operations. We're looping over the receiver, over the sources. And now the only extra is that we're storing it, but that's one JVec.
It's not quite the same. You do a lot more solves when you're forming JVec, when you're forming the J transpose. You do one solution for each data point.
Per receiver, you mean?
Yeah, for each individual observation for each receiver. When we're doing it implicitly, we only do it once per receiver object.
I'm doing it only for one per receiver object.
But there's an implicit, so when you get back that receiver, like that J, or when you get back that receiver projection, you're doing it on the entire projection matrix, right? The array of that projection matrix. So you're doing the solve on a matrix, on a bunch of right-hand sides at once. Whereas, so you repeat that solve operation for each right-hand side, essentially. It happens inside of Paradiso, but it does do that. Whereas when you call it on the implicit, it does the projection matrix times a vector first, and then only does one solve.
Yeah.
Okay, so maybe you're right. Yeah, we'll have to double check that.
Yeah, so that's so like the number of solve for forming J in our case is the number of data. So you got millions of data, then you need to solve millions of times. So that's where
no, we're doing AM on the projection of RX, and if RX has multiple data, we're doing it all at once.
It's RX all at once, or every receiver for every source.
No, we don't need 2 loops.
No.
No, I think there's a problem, I guess, because that's what it's supposed to be. So solving, like, actually, if you want to form J, think about like a J, it's an n by m matrix. And then it depends on which way you solve. So you solve either on the model side or you solve on a data set. So for like, you need to solve for a single data. Like that's
No SUG, man, no SUG, because we're appending blocks of data at a time. We're appending blocks of the J matrix. It's multiple data at once. It's however many data per receiver. So we're looping over receivers. That's it.
I think there's a little bit of a fundamental difference here that we're trying to iron out between the two of us.
Yeah. But that, yeah, Dom, I think I made a point at some point. Suppose you got your receiver object have a multiple locations, then it's not one solve. Like you need to, like let's say your receiver object have 10 points, you need to solve 10 times. So
Okay, sure. Yeah.
Yeah.
Whereas
I see that.
in the implicit version, it only does it once for all of those. Like, even though there's a bunch of receivers, it does that vector multiplication first and then does a single solve instead of 10 solves.
Okay, that's possible, yeah.
Yeah, I'll take a look at DC code that and see if I can find part, see how you're doing.
It's so at one point it's just that it when you're forming the full matrix, it does a 2 array thing instead of doing P transpose times a vector. Just does P transpose 2 array.
Well, let's look at it and let me know if we can streamline it. But
I don't think there's any other way to get around it.
Yeah, well, that's the cost.
It only does it once, I thought.
I only see it once, but maybe SUG is right. I'm not the specialist of the sensitivities. You guys go ahead.
I can show it right here.
Yeah, go for it. You on the tiled simulation, yeah?
I'm just in J transpose, like in the simulation part. So this is the part where it does what we're talking about. So if V is none and it's forming the full, or so if V is not none, it does the P transpose times V. So this result will be a vector, a single vector here.
But it doesn't have to, right? It could be multiple stack vectors.
Like this will be a single vector.
What if your receiver has multiple data attached to it?
It'll still be a single vector.
I don't understand how that works because our sensitivities at the end have the dimensions of n data by n cell.
It's just the implicit multiplication part. So this is when when you're actually multiplying, this is the implicit part. This right here is the sensitivity when you're forming the full sensitivity matrix. So this is
a matrix.
Yeah, this is a full matrix here.
Yeah, so that's what I meant. So when we're solving JET-VAG, we multiply the vector, but when we're forming J, we multiply the matrix. So I mean, if you are considering that as a one solve, then you're right. But it's literally a multiple solve. Let's say you got 10 points in your receiver, then that actually doing a matrix vector product 10 times.
I see. Yeah.
But I think as long as you're doing that, you're correct.
I gotcha.
Right.
Yeah. I see what you mean. Yeah, no, totally.
What's happening there?
So inside Paradiso, there are more operations happening in the getJ than it's still a single call, but internally there's more happening. I totally get you. Yeah.
It's actually much faster. I'm not sure why, but then just looping over iteration.
Paradiso is more efficient at splitting those things up in parallel.
It's going to be in C too, right? Like we're not doing it in Python loop.
Then calling them individually in Python.
For sure.
Okay.
Oh,
now that we're all on the same page on.
Now I understand.
Yep.
Like that, it turned into a tutorial. I just learned something.
That's why we're a group. The guys know their shit.
We're moving forward.
Did anyone else have any other quick updates or agenda items they'd like to discuss?
Actually, speaking of that MT stuff, I got very similar problem. I could actually quickly share my screen. Let's see if I can. So actually, it's literally a same problem. in Airborne EM and sort of what I'm doing. So I do a 1D stitched inversion in Airborne EM. So you got this profiles like this. And the definition of model is in the vertical profiles. So I think it's same as MT, I guess. So if you have a multiple station, you do a 1D inversion, you got vertical profiles of the resistivity. So that's the starting point. But if you think about the volumetric footprint of that resistivity is much, much larger, I guess. So I think it's not just like, I don't know how you define that. Let's say you put it in a 100 meter block, but it'll be much larger. And I'm not sure, like maybe at deeper depth, it may increase even in the MT case. Not sure, like we probably need to look at the sensitivity function. But when you're going back to the 3D, you need to think about, you can think about it as a volumetric averaging. So suppose you start from the 3D grid, and then you develop an averaging function, and then define that on vertical profiles. So that's your for problem. And once you have that for problem, you may want to go back for it like this. So that's your result of MT1D inversion. And then you can build a 3D model you could use as a starting model. So yeah, it's basically the same problem. I'm not using this as an initial guess, but that's not my final product. But it's basically the same problem. So it might be an interesting application. Other than that, I was I'm kind of working with quite a bit with geostatistics and people doing geostatistics, and they have like a very similar inverse problem that we're doing, but their regularization is a variogram, and so there are a couple of applications of it is basically switching our regularization matrix with their covariance matrix. Anyway, so it seems like an interesting avenue, and adding their geostatistical regularization function into SimPEG might be an interesting application to add. Anyway, that's what I'm doing in these days.
Taking out the box.
Cool.
So how's the MT1D? Is it fast enough? Is it good?
So the analytic one, or the
I was talking about SUG's example. Was it satisfactory?
What do you mean?
In terms of runtime and the result makes sense. Runtime is good. What do you think?
So that's where I had a bit of runtime is not too bad, like I don't know, less than 10 minutes. But because once you form that averaging matrix is forming averaging matrix is a little bit expensive because you need to search over but that's sparse matrix, so we can store it. Actually, the major cost was forming the regularization function and every iteration. So because it's not necessarily very cheap, and that was actually the major cost. And anyway, so I was thinking about what can we store when we're moving to a bigger problem. But maybe at that stage, that may not be a major cost, like just solving the physics may be the major cost. I wasn't sure whether that's needed or not. Anyway, like when things big, everything costs. So we need to be careful, even forming W. Whatever. Yeah, it works well. I was pretty happy.
Sweet.
exciting. Well, I believe that's a comment on our meeting, unless everyone has anything else. Touch base again next week, and over the, just reach out if you have questions as well. The other thing is, I was kind of entertaining the idea of hosting almost like an office hours for SimPEG related stuff. A time when okay, I would be available if someone else wants to be available or something, just to have people pop in and ask questions on random items. If people think that would be a useful thing, just to be able, oh, hey Joe, what are you thinking about this? Or hey Lindsay, what are you thinking about this? Or
Yeah, we can. That's fine. I mean, obviously office hours are only for North America. But,
Yeah.
sorry if you live elsewhere in the world. Too bad for you.
That'll be pretty
But
wild.
just kind of a, I don't know, at least a dedicated time for people to, oh, I can ask questions or something without any worry.
That's good.
I'll-
And who's for like who's it for? Is that like it's for our group or like more people on the outside?
It could be for anyone, I think, if it's just like, hey,
Yeah.
yeah. So just floating the idea. With that, I guess I'll see you guys next week. And as a reminder, as I brought up at the beginning of the meeting, for those who weren't here, I'll be hosting a coding session party thing next week, next Friday afternoon. So we can start with some coding, maybe play some games later or something, socialize a bit.
Maybe to come back to Dom, the chat events, next week you have consortium meeting and I'm gonna give there a quick, I don't know, 10-15 minute intro to the command line interface. If people are interested, how it looks like, I could repeat that next week or the week after, if there is time.
Let's plan on it next week. I don't think we have any other plans. So,
cool.
okay.
So now I have it ready anyway, so it doesn't cost me much more.
Exactly. Reuse.
Reuse, exactly. Recycle. Save
Don't
the planet.
reduce though. Never reduce. Keep producing, Peter.
Okay. Take care, everyone.